All right, so section 6-4, we got to fill in these blanks on this vocabulary at the top. All right, so the first one, it says a system, again, a system is two equations with two variables. It says a system with no solution is, let's see, we're going to call this, it's called inconsistent. So if there's no solution, the system is inconsistent. Then the second asterisk, so this one, this is a system with at least one solution. So it could have either one solution or it could have infinitely many solutions. That is called consistent. All right, well then if it's consistent and it has one solution, that is called independent. And then the last one, if it's consistent with infinitely many solutions, it's called dependent. Now let's go through and summarize those, what they mean graphically. So again, you guys have the vocabulary words up top here. But let's look at these graphs. All right, well, we know from when we started this, if we graph the two lines.
Mr. Zimmerman.
What's up?
Can you go back? You're going too fast.
Oh, okay. Yeah, I can leave it. I'll leave that on the screen. I'll put this on the bottom for you. There you go. Okay, so graphically, if we solve the system graphically, we were looking for the point where the two lines hit each other, right? That was our solution. Now that solution is the point, it's a point, but it's actually an ordered pair, x comma y, right? That's one solution, is that ordered pair, x comma y. So what you're going to write on top of this one then is you're going to write, this one is one solution. Let's do this. So this one is one solution. Well, if it has one solution, then from above, we know that that's consistent. And it's independent. All right. Then the next case, the case in the middle there graphically, that looks like it's only one line, but actually that is the system graphed already. So what they did is they graphed the solutions for the first equation, and then they graphed the solutions for the second equation, and it was the same line. So the two lines are right on top of each other. It looks like there's only one there, but there's actually two. So maybe I'll do this for you guys. Let's do, so here's all the solutions for the first equation. And then here's all the solutions for the second equation. So the two lines are right on top of each other. Well, that means that every point on the lines is a solution, so there's infinitely many solutions. Now you don't say that the answer is all real numbers. It's not. It's just the points that are on the line, okay? The points x comma y. So this middle one then, this one is, this one's infinitely many solutions. Here, let's try to bullet these for you. So infinitely many solutions, that other one was over here. All right. Well, again, from above then, if it has infinitely many solutions, well, then it has at least one solution. So that would be consistent. So it's consistent. And this one is dependent. Now remember, each solution in that case would be a point on the line, okay? It'd be the point x comma y. It'd be an ordered pair. And there would be infinitely many of them. Now the last case, graphically, you guys can see that the lines are parallel, right? That means they have the same slope. They have different y-intercepts, but they have the same slope, so they're parallel, which means they don't touch each other at all. So if the lines don't hit each other, then there's no solution. So the last one here is no solution. So if there's no solution, then that's just called inconsistent. All right. Well, then what would that look like algebraically? Graphically, we could, if we wanted to, we could graph each line and see if they hit each other, or if they're right on top of each other, or if they're parallel. But algebraically, I think we'd probably prefer to do it that way. So if we're going to solve these algebraically, we're going to use the other two methods we learned last week, which were substitution and elimination. So let me slide this up a little bit. All right, so algebraically, we're going to solve the system how about this? I'll just put solve using substitution or elimination. All right. Well, if we're solving using substitution or elimination, then if you get a solution like this first example right here, if you get a solution, remember this is the x and this is the y. Well, then you can see that that's the case that we have up here, right above it. So if we get one solution, then it's consistent, independent. I'm just going to write down one solution, okay? I'm not going to rewrite all those again. So there's one solution. So that's really what you're going to do in today's assignment. Is you're going to classify the system. You don't have to find the solution. You just got to tell me, is there one solution, no solution, or infinitely many? And then you have to be able to tell me whether that's consistent, inconsistent, dependent, or independent. Well, if you're solving one of these problems for the middle case here, for this one, if you're solving either by substitution or by elimination, and all of a sudden all the variables cancel out, and you end up with a number is equal to itself, like right here, 0 is equal to 0, that's a true statement. So if you end up with a true statement, then you know that there's infinitely many solutions. So for this one, I'm just going to write IMS. And what I mean by that is infinitely many solutions. And then the third case, again, that's where the two lines are parallel. If you're solving either using elimination or substitution, and again, all the variables cancel out, and you just end up with a number is equal or a number is not equal to some other number. If you get a false statement like this, like 0 equal 5, that is false. If you end up with a false statement, then you know there's no solution. Now, if you don't want to write out no solution, you could also use this thing. That means also, that symbol right there means no solution. All right, so then we got to get through these three examples. You ready? So let's look at the three examples. So then again, we're not really interested in what the solution is. We just want to know if there's one, none, or infinitely many. So I'm going to let you guys decide. If you looked at this first system right here, what would you use on this one? Would you use substitution or elimination? Somebody can unmute and tell me.
Substitution?
Yeah, I'd probably use substitution on that one. Hold on, I gotta let a couple people in here. Ethan, you should have your camera on. Clavon, so should you. All right. So, yeah, I would use substitution on that first one. Remember in that little chart at the end of the last lesson on 6-3, I talked about if one of the equations has a 1x or a 1y, usually that's pretty easy to do with substitution. Aiden, I need to see you on there, and you can lose that background too, or I'll have to go and reset the, I can set this so you can't change your background. Aiden. All right, so let's go ahead and do this one by substitution. So I think I'm going to solve the top equation for x. And again, the reason we're using substitution is because one of the equations has a 1x or a 1y. That should be pretty easy to solve for x, that top one. You could solve the bottom one for 1y if you wanted to. So here's my 1x right here. So all I have to do to solve for x then is I am going to subtract 3 on both sides. So then my top equation is going to become x is equal to 3y minus 3. All right, well then if I'm doing substitution, I'm going to take that and I'm going to substitute that quantity 3y minus 3. I'm going to plug that in for x in the bottom equation. Right there. So that's going to look like negative 1/3 times the quantity 3y minus 3 plus y is equal to 1. Okay? Now we just got to solve that for y. So we have one equation, it only has one variable in it, so we should be able to solve it for y. Now I'd be tempted to possibly multiply both sides by 3. Because if I multiplied by 3 over here on the left-hand side, these 3's would cancel. But then I'd have to also multiply that y by 3, and I'd have to multiply the right-hand side 1 times 3. But on this one, I think I'm going to go ahead and distribute. So if I go to distribute here, I'm going to distribute the negative 1/3 times the 3y and the negative 1/3 times the negative 3. Now, the reason I chose to do that is because 3 is divisible by 3, right? You got a 3 on the top and a 3 on the bottom. So as long as these numbers right here, this coefficient of y and this number right here, as long as those are divisible by 3, I'd go ahead and distribute. Now, if that number right there was like a 5, I probably would have not distributed, because then you'd have 5 over 3 and you'd get fractions in your problem, okay? So if I had a number that was not divisible by 3 right here, then I probably would have multiplied both sides by 3 over here, okay? But I'm going to go ahead and distribute. So negative 1/3 times 3y, well, the 3's are going to cancel, and I'm just going to get negative y, or negative 1y. All right, negative 1/3 times 3 is negative 1. And then don't forget to distribute the negative 1/3 onto this 3. Well, again, those 3's are just going to cancel. So that's going to give me a negative 1/3 times a negative 3. The 3's are going to cancel, and I have a negative times a negative. So I'm going to end up with a positive 1. All right, so negative 1/3 times negative 3 is positive 1. And then I'm going to bring down this plus y, and I'm going to bring down the right-hand side, which is y. Which is 1. So then somebody unmute and tell me, what happens to the negative y plus y on the left-hand side? Hey, Aiden, do me a favor and lose that background, will you? Otherwise, I'll block that so you can't do that. Again, I don't want Zaborowski coming in here and writing you a nasty email. So what happens to the y's on the left-hand side, guys?
They cancel out.
Yeah, you got negative 1y plus 1y, that's 0y, so those cancel out. So these two, that's 0, okay? This one and that one. So then all you have left on the left-hand side now is you just have 1, and on the right-hand side you have 1. So the variables canceled out completely, and you get 1 equals 1. Is that true or false?
True.
That's true. So if that's true, now if you look up above here, if you get a true statement like right here, a number is equal to itself, well, we got 1 is equal to 1, right? So we got 1 equals 1, which is a true statement. So then we know right now that there's infinitely many solutions, okay? And then if you go up here a little further and read up, that also means that it is consistent and dependent. So that's what we're supposed to write. Now, I don't have a lot of room to write on there, so let me kind of write it over here to the side. So then on number 1, we're going to know that there is infinitely many solutions. And then we're going to write that that is consistent. Why did I put a D on the end of that? Consistent. And I started writing the next word. It's dependent. So that's what they mean by classify. That's what they want you to write. So this note page is going to be really important on the next test, because you're going to have to be able to look back and decide, if it's infinitely many solutions, what does that mean? Well, it means it's consistent and it's dependent. So that's your answer for this one. And now remember, graphically, that means that the two lines, if you graphed them, they would be right on top of each other. Let's go to number 2. So So here's number 2. I think this one I'm going to try to do it with, let's do it with elimination. Now remember, you guys do have the option of graphing both of these lines and deciding if it's, you know, how many solutions there are, if it's consistent or inconsistent, dependent or independent. You could always do it graphically also, but I don't know. I don't really recommend that. I just like to solve the system and figure it out that way, but you could graph it if you wanted to. So this one, I'm going to try elimination. So I need to line up the X's and the Y's. So right now, the Y's are lined up vertically, but the X's are not lined up. So I'm going to add X on both sides. So I'm going to add on the bottom equation. So on the bottom equation, I'm going to add X, and I'm going to add X. Well, at the same time, I think I'm going to subtract 4 on both sides. Oh, wait a minute. Do I want to do that? Yeah. All right. So now let me rewrite these for you. So the top equation is still X plus Y equals 5. And the bottom equation now, well, these X's will cancel and these 4's will cancel. So the bottom equation becomes X plus Y equals -4. And now if I want to do elimination, like let's say I want to get rid of the X's. Well, if this is a 1x in the top equation, then below that I want it to be a -1x. So I'm going to multiply the bottom equation through by -1. Let me get a little more room on this bottom one. It was what? X plus Y equals -4. Okay, so I'm going to multiply the bottom equation through by -1. So -1 times the 1x would give me a -1x. And then a -1 times the positive y would give me a -1y. And then a -1 times the -4 would give me a +4. And now I'm going to add the two equations together, because that's what we do in elimination. What do you get on the left-hand side, guys? Somebody unmute and tell me, what do you get on the left-hand side? Remember?
0.
Yeah, 0. If you add the x's together, they cancel out. And you add the y's together, they cancel out. Yeah, so that's good. You get 0. So on the left-hand side, you now have 0 equals, and the right-hand side, you have 9. So 0 equals 9, is that true or false?
False.
Good, so that's false. So you know that's false. So then we go up here and look at our notes. And it's this one right here, right? So if you get a false statement, we got 0 equals 9. If you get a false statement, you know there's no solution. But then you also look up here and you know when it's no solution that it's called inconsistent. So that's what we have to write down. So we're going to write, I think I can fit that down here. So we're going to write no solution. Or you could just write this thing if you want. So no solution, and that means it's inconsistent. All right, now we just got to do the third one. So let's take a look at number 3. Now, also on number 2, remember that if it's if there's no solution and it's inconsistent, that means that if you graph the two lines, they would be parallel. They would not hit each other. So let's do number 3, and we'll wrap this up. So number 3, let's see, what do I want to do with this one? I already have the top equation to solve for y. The bottom equation is already solved for x, so I think that leads to probably using substitution on this one. But I'm going to do it a little different. I think I'm going to solve the bottom equation for y. So I am going to add 3 on both sides. And my bottom equation is going to become y equals x plus 3. And then I'm going to take that result and I'm going to plug that in for y in the other equation right there. I think that'll work pretty well. So now what it'll look like, the top equation will become x plus 3 is, hold on. X plus 3 is equal to 4 times the quantity x plus 1. Then I think I'm going to go ahead and distribute on the right-hand side. So I get x plus 3 is equal to 4 times x plus 4 times 1. Then I'm going to subtract x on both sides. That's going to give me 3 is equal to 3x plus 4. Then I'm going to subtract 4 on both sides. And I'm going to get negative 1 is equal to 3x. Then I'm going to divide both sides by 3. And I'm going to get x equals negative 1/3. Now, normally on these you go back and solve for y, right? But since we're classifying them, technically you could stop right here. Because when you got x equals negative 1/3, the solution would actually be an ordered pair. You know, the x would be negative 1/3, and you'd have to go back and plug that in to find y. But right away, right now, we know there's at least, we know there is one solution, right? If we know x is equal to negative 1/3, if we go back and look at our notes up here, well, we got an x coordinate for the point where the two lines cross each other. So we know right now there's one solution, and that it would be consistent. Hold on. So we know right now there's one solution, and that it's consistent and it's independent. And the graph would look like two lines that hit at one point. And that's all you had to do is just classify it. You don't have to give the solution. You just got to say whether there's one, none, or infinitely many solutions, and whether it's consistent, inconsistent, dependent, or independent. But I'm gonna go ahead and finish the problem, I think, just for practice. So let's plug that in and find the y. So I think I'm going to use this equation right here, this one. I know that y has to equal x plus 3. So if I know that y is equal to x plus 3, I'm just going to take my x equals negative 1/3, and I'm going to plug it in right here for x. So then that's going to give me y is equal to negative 1/3 plus 3. Well, that's the same thing as 3 minus 1/3. Well, 3 take away 1/3 would be 2 2/3. And then, if you wanted to, you could have made a common denominator here. And you would have got a solution for y that would have been, what is that? That's 8/3. Or you could just change this mixed number back into an improper fraction. But that's your solution for y. So then if you wanted to, you could write down your ordered pair. Your ordered pair, let's see, your x would be negative 1/3, and your y would be 8/3. So that would be your solution right there. But again, that's not what we're supposed to do. We're supposed to write down that there is one solution, so then it's consistent and independent. That's what the directions when it says classify right here. That's what that means. So let me write that in and then we're done. If I can get back over there. Okay. So we're going to write down one solution. Which means the two lines would hit each other at one point, the ordered pair x comma y. And so since there's one solution, this is called consistent. And it is independent. And there you go, that's the answer to that one. Well, I'm going to go ahead and stop my recording here.